In section 6.1, we're going to be introducing exponential functions, but first, in part A, we need to talk about rational exponents. Alright, so an exponential function is a function in the form f of x equals a times b to the x, where a is not 0, b is larger than 0, but it also cannot be 1. The constant b is called the base, and a is the coefficient. First, we're going to plug in some values to the exponential function f of h of x equals 5 times 4 to the x. So h of 2. Okay, so h of 2 is 5 times 4 to the second. 4 to the second is 16, so this is 5 times 16. I don't know off the top of my head, so I'm going to grab my calculator. 5 times 16 is 80, so this simplifies to 80. All right. Looking at the next part, h of 0, that's 5 times 4 to the 0 power. I know that anything to the 0 power is 1, so this is going to be 5 times 1, which is 5. Okay. The first three rows right here are a review from earlier, but it's nice to keep these in mind before we go into the rational exponents piece. H of negative 3. That's 5 times 4 to the negative third power. Remember that negative powers put things in the denominator, so it's the same thing as 1 over 4 to the positive third power. 4 to the third power is 64, so it's 5 times 1 over 64, and then fraction multiplication will multiply this to 5 64ths. 5 over 64. Alright, next I want to graph h of x and state its domain and range. Let me clear the graph I had previous and see if I can make it a little smaller so you can see it a little better. Okay. It's not going to play nice, but that's okay. There you go. I had something else graphed earlier, so we'll close that. And the function that I want to graph is h of x equals 5 times 4 to the x. Alright, and that's the picture of what this graph looks like. I'm going to make a sketch of that. Just something to note is that there is a y-intercept at 0, 5, and it gets really, really flat down here on the x-axis. If we zoom out, we can see that it grows very steeply in one direction and very flat in the other. So let's go ahead and make a little sketch of that picture. The picture looked like that was where 0, 5 was. It went up, it went over. So that's a quick sketch of what that function would look like. 0, 5 is right there. Alright, I also want to state its domain and its range. Okay, so for the domain, that's left and right. So for left, we're heading all the way over. We are going all the way right as we go up because we are going out too. So we're going to hit every x value. So the domain is going to be interval negative infinity to infinity, or all real numbers. And the range. The range has a lowermost value for y. It does not go below the x-axis. It goes all the way up, but the lowest most value is going to be 0. So it's going to be 0, infinity. And it doesn't actually hit 0, it gets very close to it, so we're going to use the parenthesis there and make a quick note that it does not include. We can verify that back in our graph. Oops, that's the wrong part. Here we go. We can verify that back in our graph. If we slide our points along, they are getting smaller and smaller in x. It looks like it gets towards 0, but my computer has to round these. After I get to the third decimal place, it rounds it down to 0, although they are really 0.000. If you had 7 places and more, you'd see the 1 in the end. Alright. Is h of x continuous? AKA, does it connect through all values? Yes, it is, right? It was smooth and connected. It didn't have, the opposite of continuous would have been discrete, and it wasn't like that at all. It was smooth and connected, so it was continuous. That's going to lead us into h of 1/2. If it's continuous, then it has to have a definition for not just the whole numbers and the negatives and the positives, but the fractions and decimals as well. Okay? So h of a half, let's bring them back to my graph. There we go. Too many tabs open, sorry about that. H of a half. Okay. Give me a little point, let's see. Positive 1/2. So I'm looking at 0.5. There we go. It looks like 10 is the value. 0.5, 10. Why would it be 10? Let's think about that in a second. I'm going to write that down on my other page. So it looks like h of 1/2 is equal to 10. All right. Now, we'll come back to why it's 10 once we look at the rational exponent rule number 1 down below. The rational exponent rule says that b to the 1 over n to the n is equal to b. So basically, the 1 over nth power and the nth power undoing each other. Okay, they're opposites, returning b as the result. Okay, so rational exponents, if they're the opposite of powers, like the power 2, then they could be written as the opposite of power 2, we think about as the square root, right? X squared and the square root of x are opposites. Just like x squared and x to the 1/2 power are opposites. Okay, so that means that x to the 1/2 power and the square root of x are the same function. They're two ways of writing the same function. So we can write these rational exponents with radical signs. We're going to work more on other radicals in later chapters. For right now, we're going to look at them in numeric cases. So a to the 1/2 is the same thing as the square root of a. A to the 1/3 is the same thing as the cube root of a. And a to the 1/4 is the same thing as the 4th root of a, etc. If I keep that in mind back up here, if I was to evaluate h of 1/2, that's 5 times 4 to the 1/2. If I rewrite that as 5 times the square root of 4, then I know the square root of 4 is 2, and 5 times 2 is 10. And that is what we estimated from our graph before. 10 was the solution to h of 1/2. Okay, and again, it was a matter of understanding that 4 to the 1/2 power and the square root of 4 are equivalent. Alright, so I can evaluate these without using my calculator based on what I know about changing fractional powers into square roots or third roots into their radical form. So 49 to the 1/2 power is the same thing as the square root of 49. The index 2 is for a square root, the index 3 for a cube root, etc. So it's 7. 8 to the 1/3 power is the same thing as the cube root of 8. If you're not sure the cube root of 8, you can use a calculator, but I know that 2 cubed gives me 8, so the cube root of 8 must be 2. Negative 25 to the 1/2 power. If I think about what is the square root of negative 25, in terms of a square root, that's going to be imaginary. In this context, we don't really use I very often. We just say that the answer is not real, although it is the same thing as 5i. Negative 25 to the 1/2 power, though, with the negative not inside of a parenthesis, is outside the radical. So that's the square root of 25 with the negative outside. So that is negative 5. So parentheses make a difference, especially with those negatives. Right. Next, we have the second rational exponent rule. This one has a numerator, b to the m over n. It's the same thing as b to the 1 over m to the mth power. So if I had a to the 3/2, let me write this one out. But if I had a to the 3/2, that's the same thing as a to the 1/2 power to the 3rd power. So that's the same thing as the square root of a to the 3rd power, or the square root of a cubed. That's how we're going to want to think about them. The square root of a cubed. So if I rewrite these, the denominator becomes the index of the radical. So the radical part comes from the denominator. And then the numerator stays as a power, right? So the numerator m is going to stay as a power, while that inner piece goes into the denominator. So this is going to be a to the 3/2 is the square root of a cubed. A to the 2/3 is the cube root of a squared. If I have a negative, the negative is going to put it in the denominator. This will be 1 over, the denominator is 4, so the 4th root of a to the positive 3rd power, positive 3rd because we put it in the denominator, and a to the negative 7/4 would be 1 over from the negative, the 4th root of a to the 7th, etc. We've got a few examples here to look at. We're going to evaluate this without a calculator first. So this is going to be 25 to the 3/2 power is the square root of 25 cubed. Now I can evaluate these in either order. I can cube 25 first, or I can do the square root of 25 first. And like the parentheses up here seem to indicate, I want to do the radical first to break that 25 down. So we're going to do the square root of 25 is 5, and then we're going to cube it. And 5 cubed is 125. I don't know what 25 cubed is in my head, but if I do know that the square root of 25 is 5, I can break that part down in my head. I can still use my calculator to cube 5 if I don't already know 5 cubed is 125. Okay. This is negative 81, not in parentheses. So it's going to give me denominator 2, so square root of 81 cubed. I know that the square root of 81 is 9. It's negative 9 cubed. And 9 cubed, I just used my calculator for that one. I didn't know what 9 cubed was, but it's 729. So I have negative 729. All right. This negative is inside the parenthesis, so it means that negative 64 is going to be inside the cube root, and then it's going to be squared. Instead of negative 64 inside, I forgot to write the negative, but it's definitely inside because of the parentheses. So we need the cube root of a negative. Unlike positives, you can have 3 negatives and be negative, so the cube root of a negative will exist just fine. So if I do the cube root of negative 64, it comes out just fine as negative 4. So I have negative 4 here that I need to square, and so my answer is going to come out of that positive 16. The square is going to turn it positive. I've got a negative power in part H, so I have a 1 over the square root of 36. So it's going to be 1 over 6. All right, and then the last little piece here, the exponential coefficient. When f of x equals ab to the x, the y-intercept is, I'm not sure if we noticed that on the previous page, but let's look at this tip. A y-intercept is found from evaluating f of 0. So if I evaluate f of 0, that gives me a times b to the 0, but b to the 0 is 1, so that's a times 1, so it's a. So I will always get a whenever I plug in 0, so the y-intercept is 0, comma a. The y-intercept is 0, comma a for a function of the form a times b to the x. Now just a quick look back at the previous page. You may not have noticed that, but when I plugged in 0 to the h function, I got 5, and 5 was the a value, because the 0 power turns the base into a 1. So I can state the y-intercept of these without doing more than looking at their a value. The a value is 8 in the first one, so the y-intercept is 0, comma 8. The a value in the second one isn't shown. It's got to be 1. 1 times 3 to the x. So this is 0, comma 1. And then in the final one, it's going to be negative 1 times 6 to the x. 6 is the base, so the a value here is negative 1, and the b value there is 6. So it's going to be 0, comma negative 1.